So I just want to show you some series for which the ratio test is inconclusive. Because it might be tempting to say, oh, I don't need any of those comparison tests anymore because now I have the ratio test, but it often doesn't work. So let's just look at A, where we have the sum from n equals 1 to infinity of 1 over n. And I think, as I've mentioned, this, by the way, is called the harmonic series. We know that this diverges because it's just a p series with p equals to 1. So let's try the ratio test. Try it in purple. Works better in purple. Let's try the ratio test on series A. So that's going to be whatever the limit as n approaches infinity of that's going to be 1 over n. Sorry, 1 over n plus 1 times n over 1. So in other words, an plus 1 times the reciprocal of an. And I'm not even going to put the absolute value in because we know that these terms are all positive, so that's kind of redundant. Although technically you just remember the ratio test does require absolute value. So this is just going to be the limit as n approaches infinity of n over n plus 1, which we know equals 1. So inconclusive. For B, we have a series that is very obviously divergent. We could certainly use the nth term test to prove that series B is divergent because we're just adding up larger and larger numbers. We're raising, 5 to the power 500 is just an enormous number, and it just keeps going and going. So you'd think, well, surely the ratio test must be able to tell us that that diverges. But if we do, we just get n plus 1 to the 500 over n to the 500. That equals the limit as n approaches infinity. The way we simplify that is n plus 1 over n to the 500, which just equals that equals 1 to the 500 because this limit inside the parentheses simplifies to 1, and that equals 1. So again, that's inconclusive. So that doesn't work. And here's another one. This is one of the problems we found sort of vexing that we had to do by, we had to use either the limit comparison test or be fairly clever about how we use the direct comparison test. So you might think that this provides you with another option, but once again, we get 1 over n plus 1 squared minus n plus 1, just replacing every n with n plus 1, and then the reciprocal of an is n squared minus n over 1. So that gives us the limit as n approaches infinity. Let's be clear what I'm doing here. This is an plus 1, and this is 1 over an. So now I calculate the limit as n approaches infinity of n squared minus n over, we'll simplify the bottom, that's n squared plus 2n plus 1 minus n minus 1. So this becomes the limit as n approaches infinity, n squared minus n over, this is going to be n squared plus n. So once again, we just have the two highest powers match. So we take their coefficients. However you want to calculate this limit, that's the easiest way to do one of these limits of just power functions. So that comes out to 1, and once again, it's inconclusive. So there's this very large class of functions for which the ratio test just doesn't work. In general, the ratio test is going to work best with functions that have either powers of n or factorials or both. They can have other things in them too, but as you saw here, we were able to get an answer because we had a factorial and a power, and sorry, not power of n. We had an exponential function, a constant being raised to a power to n in the exponent. Those are the things that you're looking for the ratio test to work. Here, what we have is we have n being raised to a constant power, -1 in the case of a, 500. Then we have a couple of different constant powers of n. Those are the situations where the ratio test is generally not going to work.